All set.
Good afternoon, everyone. Thank you for attending this almost monthly webinar from C2 Smart Center. My name is Hani Nassif. I'm the Associate Director of C2 Smart. I'm a professor at Rutgers University, and this series is part of our Rutgers Infrastructure Monitoring and Evaluation RIME Group webinars series for technology transfer with our sponsor, the New Jersey Department of Transportation. Today, we have an exciting topic. It's about the use of GFRP rebars and CFRP tendons as non-metallic reinforcement for extending the service life of bridges. Our speakers are very well known and established in this area. We are hosting today Danielle Kleinhans. She's the Director of Engineering and Business at Mateen Bar, and she graciously agreed to be part of this because we're working closely with the industry to examine the applicability of GFRP rebars for New Jersey DOT. And also Michael Rosella, who's our own here, has been as Rutgers undergraduate and master's degree, and he's currently for the last couple of years been working as a research engineer full-time with the RIME group. And also the Wasim Nasruddin, he's a research associate who has been working with the CFRP pre-stressing, post-tensioning, and pre-tensioning testing. He did his PhD work about maybe four years ago, and he's been with us in this group. So this topic is very, close to what we are doing. This is, as I said, this is sponsored by the New Jersey Department of Transportation, which I'd like to acknowledge their support and their technical advice on these things. And we are still in the middle of the project, but we opted to share the results with our community. So without any further ado, I'd like to give the platform to Danielle to start on with the presentation. Thank you.
Wonderful. Thank you so much, Dr. Nassif, and really happy to be here. Thank you for the invitation. As mentioned, we're going to talk just a little bit about our company's experience with some relatively large infrastructure projects, really talk about the state of practice for reinforced concrete and some shifting paradigms when we're talking about mild reinforcing. Next slide, please. Again, my name is Danielle Kleinhans, Director of Engineering and Business Development for Mateen Bar. I did complete my PhD some 20 plus years ago on the topic of FRP for bridge construction. So as you'll hear a couple of times mentioned throughout, it's not a new topic, but we're really thankful and glad that more states, including New Jersey, are considering it for infrastructure projects. Next slide, please. The outline for the presentation today, I'll go through some various options really quickly for reinforcing bars for corrosion. I'm sure you're familiar with many of them. I'll talk a little bit about Mateen Bar as a company, give an overview of GFRP properties, then the standards and specifications that are in place for the design and specification of GFRP reinforced concrete, give a snapshot of availability in terms of sizes, etc., and then mention just a couple of case studies. So if we think about fresh concrete, right when it's placed, if we're thinking about steel reinforced concrete in this particular case, it's a really happy combination because the high pH of the concrete serves to passivate the steel in this very early and fresh condition. Next slide. However, as we all know, if we think about applying de-icing salts or in marine environments where seawater is present, those chlorides start to get to the level of the bar within the concrete. Once it reaches a certain threshold, we won't debate what that is at this particular conversation, but once it reaches a certain chloride threshold, that corrosion starts to begin, which we know causes ill effects to structures. Corrosion can also take place, obviously, because of harsh chemicals or just carbonation over time. So the steel industry has been quite responsive, as I'm sure you know, to this issue, coming up with many different kinds of coated and uncoated bars to combat this problem of corrosion. There are several epoxy-coated bars. The standard numbers are in the parentheses after each of the bar types here. If you're following along, those are the ASTM references. So there's epoxy-coated, galvanized-coated, various types of stainless steel bars. There's also high strength, which is a low carbon chromium bar. And then various options for either dual coated or metallic clad bars are actually kind of coming back onto the marketplace. But all of these options really are with the intention of trying to combat this problem of corrosion. But we think we have a better option. So if we shift to an innovative solution using GFRP or glass fiber reinforced polymer bars, we take the corrosion out of the equation completely. They're completely non-metallic, and so they will never corrode. And so that's really what we want to talk about today. The company that I work for, Mateen Bar, has been a leader in this area. There are obviously other manufacturers of GFRP bars as well, commercially available. But we've been doing this for about 30 years, really engaging on infrastructure projects globally, trying to work with the industry across the board in developing these codes and standards, which have been under development, as I said, for decades now. Talking with DOTs like yourselves about why this can be a trusted option for long-term durability, and really engaging in research, such as some of the information that we're going to be talking about here. As an industry, really happy to always support these research efforts and in advancing the codes and specifications. So we do actually have two key product lines. The one that I'm highlighting here is our higher modulus product, which would be our Mateen Bar 60. It would meet the D8505. We'll talk about the specifications in just a second, but this higher modulus product typically is used for seawalls, bridges, higher loaded or more heavily loaded structural applications. But most of the companies out in the market do actually have a lower modulus product that does meet the D7957. So we can get into those nuances here in the next couple of slides. With the requirements for Build America, Buy America coming online as well this year for composites, just want to ensure the DOTs in the audience that our manufacturing facility is located just outside of Charlotte, North Carolina. I'm hopeful that some of you that attended our tour during the AASHTO COBS meeting are on the call, but with our facility there, we're completely BABA compliant. For any projects that would be requiring that in terms of those that would be federally funded. So really what we want to talk about today is the reason why GFRP is applicable. We're really touting it for these large infrastructure projects. In particular, the decks, obviously, that are exposed to either, in this particular case, a marine environment and or de-icing salts. Obviously, many states across the country use a large amount of de-icing salts. And so this is really where, in these large infrastructure projects, we're seeing, one, the effects of corrosion, but then two, the advantage of possibly using GFRP as an alternate. And then, as I mentioned, the marine and coastal projects as well. Many areas of coastline that are exposed to harsh environments. One that we'll talk about a little bit later is this bridge that was built in North Carolina. And that was specifically the impetus was that it was this coastal area out in the Outer Banks, and they were having to come back quite regularly and repair and replace the structure. And so they decided to transition to GFRP. So what is GFRP? Glass Fiber Reinforced Polymer. It's manufactured by a pultrusion process that is outlined in the schematic here at the bottom. If we look at the left-hand side of the figure, we see the spindles of glass roving. So think of the glass fibers. They're pulled through a guide plate and then pulled through a resin bath. So they're completely impregnated with the resin. They'll come along further down the production line here, the pultrusion line, and go through a preformer and then a forming die. This forming die also cures it, it heats it, and in this particular case, obviously, it's forming it into a round diameter bar that is in the shape of the rebar. Obviously, it's coming down the line and getting cut off at whatever length is required. So the GFRP mechanical properties are different than steel. It has a higher tensile strength, but a lower stiffness. If you look at the figure on the right-hand side, this is a very simple representation of that stress strain curve, the red line representing a grade 60 steel bar and the blue line representing a GFRP bar. So you can see that much higher tensile strength where that failure load is, but you can also see the slope of the line there representing that lower stiffness. Um, it is linear elastic up to failure, and so there is a limited ductility. This is accounted for within the codes. And it is anisotropic, with those fibers going along the longitudinal direction of the bars. The properties across the bar or across the section are slightly different than they would be longitudinally. So a few things to consider during the design. But again, it is stronger. It's also quite a bit lighter. It's about 1/3 to 1/4 the weight of steel. And so you're getting this very high strength to weight ratio that can provide benefits if we're thinking about transportation, if we're thinking about construction, and those efforts of moving the material physically around the job site. Again, it is non-metallic, so it will never corrode. And as we'll talk about here in a couple of slides, there's a whole suite of recognized codes and standards for GFRP. Because of this non-corrosive property, it is highly durable and offers cost of savings over the lifespan. So this life cycle cost savings, the ultimate measure of sustainability or durability is that you don't have to replace the structure, right, as often. And so we'll talk about sustainability further into the presentation as well. But again, that longer lifespan will really serve for the reinforced concrete projects here. And then also for any application that requires a non-metallic or electromagnetically neutral. So think of toll plazas, et cetera, MRI rooms. I know we're talking about infrastructure here, but anything where you're having sensitive equipment, it would be one of the only options in terms of reinforcing. So the codes and standards, I'll mention on the next slide, but the material specifications through ASTM are in place. The codes and standards for the design are in place through AASHTO and ACI. And then there's actually, it's included in the masonry code as well, just as a secondary point. So these are the codes and standards, ASTM D7957. I also mentioned D8505. Those are the two material specifications. They outline not only the physical properties, but the mechanical properties and durability properties that the GFRP must meet. That's all included within the test specifications. There's an AASHTO guide. The second version was published in 2018, so that is also not a new document. That's been out for quite some time. And then most recently within ACI 440, which can still offer some guidance, certainly to infrastructure projects, the building code requirements. So ACI 440 is akin to ACI 318, as you would be thinking about for steel reinforced concrete. And then a companion guide document that walks through some of the design procedures and considerations, and then also a construction specification that could be used to think about the handling and the field implications of GFRP. So we and many others across the industry, as I mentioned at the beginning, are quite active in a number of different groups here you'll see listed on the slide. Really trying to advance the best practices and drive the innovation for GFRP, making sure that the codes and standards are advancing, that they're representing sort of the global state of the industry. But it's really important for us and many others, as I mentioned, within the composites industry to be active within ACI, AASHTO, ACMA, et cetera. And with that, some of those activities through AASHTO COBS, AASHTO materials, et cetera, we've been talking over the past several decades with several departments of transportation, and you'll see 6 of them listed here that do have approvals. We could add to this list Texas, which just came online, I believe it was earlier this year. And then Virginia and California also have provisional approvals. So more and more states are looking at GFRP as an alternate, really considering where they want to specify it and how they want to specify it. And so that's part of what we're working through is to talk to the Departments of Transportation and provide that trust and that assurance of what the industry has been up to in terms of the codification. So if we think about availability, a Teen Bar 60 is available in standard steel diameter sizes. So it's specified the same, number 3 to number 8 in our particular case. The ASTM goes up to number 10. And there's actually discussions to increase that to a number 11, but that's not in the specification yet. Our stock lengths are 20, 30, and 40 feet, though we're working on technology to get out to 60 feet, and then theoretically it could be as long as you want, given the manufacturing process. Really, the limitations are logistics and transportation. Um, and one sort of shift as well to mention here, it is priced per linear foot rather than by the pound. So that's just sort of a mentality shift if we're thinking about how we're calling for the material in the project documents. We do offer prefabricated bends. As I'm sure you're aware, the GFRP cannot be bent in the field. It must be formed within the manufacturing facility while the resin is uncured. But really, any of the standard bend shapes that you would be used to ordering, you can see some stirrup type shapes here. We can certainly have circular hoops and spirals, and that would be just considered within the order. Obviously, in this particular case, we're really serving as the manufacturer and the fabricator for the GFRP bars. So this is just a little bit further there. Again, forming within the manufacturing leads to really precise tolerances. You can see some of the shapes there that are possible. And again, just that reminder for no field bending. We offer full traceability and data transparency as well. According to the ASTM specification, each bar must be marked with a lot number that includes the ASTM specification to which it was manufactured, the manufacturing facility, and those details. That lot number then can be used to cross-reference with an example certificate of analysis that you see on the screen here that really outlines for each of the test requirements within that material specification what the requirement was, and then what the test results were for that actual batch or that actual lot, in this particular case, of the GFRP bar. So offering that full traceability should there be any questions on site. We'll get to the couple of project examples now. The Liberty Bridge in Ohio was one that was completed in 2021. 8 spans of concrete, reinforced concrete deck here. Quite a long structure that used a significant amount of Mateen Bar 60. Really good, constructability from the contractor perspective here, and it was awarded an ACEC design award there in Ohio. Harker's Island Bridge, I had mentioned earlier, it's the world's longest bridge built without steel reinforcement. Again, it's located in the Outer Banks of North Carolina. It uses more than 1.5 million feet of GFRP bar. There is really no metallic reinforcement. I can't stress that enough, apart from the barrier rails. The pre-stressed beams themselves use carbon fiber for the pre-stressing. And then the GFRP bars for the mild reinforcing in those girders, and then fully GFRP reinforced in the deck. It was really, as I mentioned, a response to the fact that they were coming back to this site every few decades and replacing the structure and opted to use the GFRP in this particular case. Then the low battery seawall, another project in the Carolinas, this one in the city of Charleston, South Carolina. They replaced the full seawall that you can see in the lower right-hand picture with the GFRP for repair and basically raising the elevation of the seawall as we're seeing the seawaters rise across the globe. One of the things that was noted in this particular case was it was a phased construction project, and by the time the contractor got to the 4th phase of the project, they were able to complete it in just 7 months instead of the predicted 14 months of construction time. So that's really a testament to that lightweight. They were able to pre-tie cages. You can't quite see them in the small figures here up in the upper right-hand side, but they were able to pre-tie cages, use smaller equipment, smaller crews, and really just get it done quite a bit faster than anticipated. So that was a real benefit to the city there. I said I would talk about sustainability a bit here. So there are environmental product declarations. So if that's something that you all are requiring for GFRP. In full transparency, Mateen Bar is working on ours now, but there are published EPDs for GFRP materials. And if we look at those EPDs and we consider a comparison to steel, comparing to the industry average EPD that's published by CRSI, we see about a 10% decrease just in terms of the raw material. Again, if we translate that to fewer trucks, more product per truckload, we're saving in that distribution phase. If we're looking at the use case, obviously that longer service life and that lower maintenance will really show up here in the sustainability considerations. And then recyclability, we haven't seen service life ends for reinforced GFRP reinforced concrete, but it certainly could just be crushed and reused with the concrete. So this is one of the last slides here. Major differences in design, obviously the corrosion resistance, lightweight, easy to cut. So it's lighter, it lasts longer, and it will cost less. We do need to consider some of the differences in design, which I think some of the subsequent slides are going to talk about in terms of the linear elastic to failure, lower modulus, etc. But those are all considered, as I mentioned, in those design provisions. Next slide. I think that might be the end. Yeah, perfect.
Yeah. All right. Well, thank you, Danielle. That was excellent and a really great overview to lead into this section. So what I'm gonna once again, I'm Michael Rosala, and I'm going to be talking about some GFRP lab testing that we did to introduce how GFRP is tested, as well as a behavior overview from that testing that we did in lab, and kind of explain briefly how that incorporates into some of these design differences from typical steel construction. So we chose the most prevalent ASTM standards to test, specifically for strength testing. There's also a large amount of durability testing, which was a little bit out of scope for our lab. So some of those tests are the tensile testing of the GFRP bar itself. So that's tensile modulus and strain testing, as well as bond pull-out testing, which we specifically use NJDOT HPC for the bond pull-out testing, as well as a flexure testing to get an as accurate overview. And we also use it rebars that we would anticipate to be used in New Jersey, being Mateen bar and MST bar, and a couple others as well. So all GFRP must comply with ASTM D7957, which we'll briefly touch on. And it's mainly controlled by two design specifications that Daniel went over previously, but that's the AASHTO LFRD Bridge Design Guide specifications for GFRP reinforced concrete and ACI 440.0.11. So we're going to get right into it. So we're just going to go over briefly some learning objectives. I want to show the ASTM testing. This will give us an idea how it behaves, specifically in NJDOT high performance concrete at maturity, and how these properties are reflected in code and how they're used. So, as she said, also the brittle nature of GFRP must be accounted for. And it differs from steel in a couple fundamental ways, but this can be compensated for and worked around, of course. And as well as showing differences in flexural behavior of reinforced sections, a quick bond strength testing overview, as well as a brief introduction to these design differences and a life cycle cost analysis. There's some interesting cost gains over the long term that can be realized from this technology. So there is that standard ASTM D7957 that sets the the minimums. So these are fairly low. This was implemented a while ago. The technology seems to have improved a decent bit. And the typical structural grade GFRPs that are used currently in infrastructure projects are fairly significantly stronger. They have high modulus of elasticity compared to the earlier bars, better ultimate tensile strain, guaranteed bond strength that, from what we can see from literature, is approaching that of steel. So a lot of the considerations with the early rebar have been addressed with better better designed for the ribbing, etc. And as of course the ultimate tensile strength has increased a decent bit. And you can see that compared to steel, it excels in strength, tensile strength, but the modulus is much lower, so it's a less stiff material. And maybe most critically, it strains a lot less. And you can see that in the graph on screen. You can see the linear behavior of GFRP up till failure, much lower ultimate strain, but steel has the characteristic ductility that we know and we design around that's very familiar, where there's this very drawn out ductile failure. So some design changes are used to compensate once again. So our testing involved coordination with industry partners, the GFRP rebar suppliers, as well as our industry partner Clayton Concrete, which provided NJDOT HPC for our bond testing to these GFRP bars, as well as flexure testing to try to um, establish and showcase this behavior to the audience. And currently, we have ongoing large-scale testing. It's a testing series involving post-tension decks. And we also have Wasim here, who is an extensively tested non-metallic tendons, and there's a couple slides on that topic as well, including this large-scale testing. So just to get into some of the flexure behavior, you can see the flexure test on the top left, and as well as the resulting behavior from these sections. They were tested with GFRP and steel with different rebar configurations, going from number 3, 4, and 6 to represent under reinforced and over reinforced sections. So we can see that with the GFRP, all of the beams failed in a brittle manner, as is characteristic of GFRP reinforced sections. So the over reinforced sections broke in compression, so a brittle failure, so concrete crushing, and the under reinforced section ruptured, and that's a very brittle failure that the code tries to eliminate because it is a more sudden failure mechanism. And we can compare this to steel, where an over reinforced section crushes at the top, as you know, in the compression block zone. And when it's balanced reinforcement, like with the number 4 or under reinforced with the 3, we see a very prolonged ductile failure where the load gradually decreases over time as opposed to a abrupt failure event. And we can also see an example of the rupture. It's a more sudden decrease in strength capacity. And in this case, it seems to be a delamination of the composite fibers for the matrix in the bottom left image. So going into the data from this test series, we can see the raw data and the idealized results that are just the cleaned results based on the slopes. So we can see the more drawn out behavior of the steel rebar as expected. Once reinforced, we see the steel, a little thunder, excuse that. We can see a more brittle failure for the over-reinforced steel section and a characteristic brittle failure or concrete crushing of all of the GFRP members. So, but we do see that for the rebar size, it does reach a higher capacity. So it is an excellent material in that regard, and that's why design compensates for these differences. So going into bond strength testing, we ran bond strength testing in our lab. We made a tensile testing machine jig, as well as it uses a precision displacement gauge to measure slippage. We use NJDOT concrete specimens with the embedded GFRP rebars with anchorages, and you can see the setup on the left and the sample setup on the right. Only a portion of it is bonded to increase the accuracy of the test. As far as our in-house results, we're just getting started with this series, so results aren't fully compiled, but we do have a good representation. We can see that with an HPC and these modern rebar, it well exceeds the minimum bond strength. It's fairly excellent bond. You can see the actual structure of the rebar. You can see the ribbing or the helically wrapped structures that are commonly used in high grade rebar today, and you can see the embedment line. You can also see a little bit difference in the behaviors. While both of them reach fairly similar peak bond strengths, a little bit of the behavior is different. Maybe ground rib holds that plateau for a little bit longer at the higher rate. But we'll further expand testing and get control samples with steel and larger diameter rebar with a modified setup. So going into our large scale testing that's currently ongoing, we're doing a barrage of testing on different large scale slab specimens. We're combining steel and GFR reinforcement, as well as steel tendon and carbon reinforced polymer tendon testing. So we're trying to get a full overview really of this this material, and we're investigating the use of fully non-metallic and corrosion-proof um, bridges, like we saw Danielle showed in that bridge, which I believe it was the Harker's bridge, but an excellent example of these two things combining to make a fully corrosion-proof, typically marine structure. So I'm going to turn it over to Wasim a little bit to talk about the CFRP. Um, so
Yeah,
go ahead.
thank you, Mike. This is Wasim. I'm here to give a small overview on our previous work involving CFRP tendons. So this work was started like 7 or 8 years ago. It was part of my research. So the work involves CFRP tendons used as a pre-stressing material for beams. We used two types of CFRP tendons, the CFCC manufactured by Tokyo Rope and the CFRP manufactured by Higgs Brothers. And you can see both CFRP tendon types. One of them is more flexible and it comes in coils. The other one resembles an FRP bars, but they both have very similar properties. An ultimate strain of 1.7% and an ultimate stress of 320 up to 400 KSI, which is much higher than that of the steel, which is around 270 for the tendon and around 80 for the bars. Next slide. Okay, so this is our testing setup. This is a schematic drawing for our testing setup. We do mainly flexural testing to investigate the flexural behavior of beams. And for this experimental program, we used we built two different sets of beams, one as simply supported and the other one as a continuous beam. So for the simply supported beam, we used the CFRP tendons as straight tendons, and we used both types of tendons shown previously, the Aslan and the Tokyo Rope one. But for the continuous, you can see that the tendon profile is parabolic because we have two spans, and the tendon shall be in the tensile and the at the maximum moment location. So a parabolic profile cannot be achieved with the Aslan, which is not a flexible bar, not a flexible tendon. So we use the CFCC tendons for the continuous beam. And we had several beams tested with different combinations of tendons. We used both steel and CFRP. We used as bonded and as unbonded tendons, and we made a full comparison between the two tendons to see how they affect the flexural behavior or other behaviors. Next slide. Okay, so these are the steps involved for the experimental program: building a formwork, then steel cages, then pre-tensioning. That's exclusively for simply supported beams. It is done in a pre-stressing bed, but for the continuous beam, it is done on the testing setup itself. We have we use strain gauges to monitor strains, LVDTs for deflection, and tilt meters to measure rotations at critical sections. And we also monitor the cracking behavior using micro cameras. Next slide. Okay, so this is a summary of what's the main difference between beams pre-stressed with CFRP and beams pre-stressed with steel. And so basically, CFRP has a higher tensile ultimate tensile stress, but it fails at a much lower strain, which is 1.7%. Compared to 5% for steel. And that results in a difference in the ductility of the beam. Although beams with CFRP, pre-stressed with CFRP tendons, reach higher ultimate loads, they fail at lower deflections, almost half the deflection of that of a beam pre-stressed with a steel. As for the cracking behavior, beams pre-stressed with CFRP show better crack closure after the test is done. So cracks, because of the linear elastic behavior until failure in CFRP tendons, because they do not yield. So that elastic behavior could close the gaps caused by the cracks. And that's shown here. And if you see in the corner, there's a huge drop in the average crack width in the two beams pre-stressed with FRP tendons as opposed to that pre-stressed with the steel, where there is almost no drop in the crack width after the test is concluded. Next slide. Okay, so in the previous slide, we were showing the beams with bonded FRP tendons. Here we have a mixture of different steel, different tendon types, and different bond types. So whether bonded or unbonded, and we use bonded steel with unbonded steel, or with unbonded FRP, and vice versa. So we have 4 different beams, and there is really no difference when used as an unbonded tendon. So if the FRP tendon is used as an unbonded tendon, it behaves just as good as steel, ductility-wise, because that was the problem with bonded CFRP. But here, whenever we have 2 beams with bonded CFRP, and it's likely that those beams will fail and tendon rupture, depending on the design. This is not a desirable type of failure, but it's likely that it would happen because of the small ultimate strain in beams and CFRP tendons. And whenever the beam is pre-stressed with a bonded tendon, it's likely that this ultimate strain will reach much faster than if it was used as an unbonded tendon. So this is the okay, another set of beams. Yeah, go please. So this is another set of beams. This was with the Aslan with Aslan tendon, and as mentioned previously, this is used only as a straight tendon, only in simply supported beams. And the behavior is not different from the CFCC. Both can be used as straight tendons. So whatever conclusion we had, the lower ductility, the higher ultimate strength, the better crack closure compared to steel counterparts, still stands with Aslan tendons as well. And that concludes the
Yeah, sure.
overview on CFRP. Back to Mike.
No, I appreciate it, Wasim. That was
Yeah.
a good technical overview of the differences with CFRP and steel. So that leads into the design differences for GFRP in general and steel. So we looked into a little bit on in the previous slides the differences in the behavior, and so now we can kind of better understand why there's differences in the design code. So the design philosophy for GFRP includes is basically built around a strength reduction factor of 0.65 or 0.75 for the compression controlled failure. Um, you could, if you know, with steel reinforcement, that's the more brittle failure mechanism, so it has that larger reduction than ductile failure, but it's inversed. So compression controlled has a little bit of a warning. There's a little bit of a slower process compared to rupture of the tendons or the rebar. So that's disincentivized or penalized rather using the code all the way down to 0.55. So, there's that very large reduction. There's very little strength loss over time with these rebar, and that's already corrected for with a alkali degradation environmental coefficient. So, since this product has this brittle failure, it's penalized multiple times to ensure that failure is statistically um, accounted for. Another thing to consider is the differences in thermal design. Our GFRP is a little bit more sensitive than steel. It begins to become affected at 150 C with significant reductions in strength past 250 C. You can see in the bottom left the reduction factor in strength. You can see steel leads that graph having high resistance to thermal damage. So this becomes relevant in fire, for example, in a bridge deck or an overpass. If there is, let's say, a truck fire or car fire, this can become very relevant to that structure. So there are some additional design requirements, adjusting the cover, adjusting the clear cover rather, or adding insulation to critical areas, mainly being against the embankment or the abutment that it's resting on, or critical sections like splices. And the reason why those sections need to be protected is because bond strength is susceptible to fire damage. It undergoes a fairly significant reduction. So additional detailing is used to compensate for that and give additional time to resist that damage. So this also something to consider is creep rupture under sustained loading and fatigue rupture under cyclical loading. Um, GFRP reinforcement should be proportioned or shall be proportioned that the sustained design strength does not exceed zero point 0.3 of the design strength. And this is outlined in ACI code 440.11. And that goes into our section on the life cycle cost analysis, as Danielle was saying, and Wasim mentioned, and we keep saying throughout this whole presentation, this material is impervious to corrosion. So in areas where that's relevant, so heavily salted sections or coastal, which New Jersey has both, this is definitely a consideration. It's found that there may be a slight upfront cost increase due to all of these different design considerations, maybe more reinforcements required, but universally, cost savings are realized over the long term of the structure. Some literature reports are out. There's a lot of it's a very complicated thing doing these LCCA analysis. It can be totally different for different metrics, different bridge lifespans, individual structures and regions. So it's hard to find a comprehensive study for exactly what you're looking for. But we do see consistently over the long term of a 65 to 100-year structure lifespan, you see a 20% to all the way to 50% reduction, mainly depending on how many bridge deck replacements are incurred during that time span. With GFRP, theoretically, it could go on for a 100-year lifespan before something major bridge deck replacement is required. Um, it touts a much lower maintenance costs with a reduced maintenance schedule and different benefits as well. So that's going to be the main overview for the life cycle cost analysis and into the acknowledgments. And the authors would like to acknowledge the New Jersey Department of Transportation and especially the Bridge Resource Program, which a lot of this was represented in this presentation, and as well as our industry partners who we couldn't have done this without, being Clayton Concrete, Mateen Bar, with Danielle's assistance as well, MST Bar, and for all their material support on making this research possible. So big thank you to all of those people that were part of that. So, Professor?
Thank you, Mike, and Daniel and Wasim for being on time. I think we have plenty of time for a couple of questions. So, are there any questions from the audience? I haven't followed the chat. And Lizzie, if somebody wants to do a question over the microphone, could there be a way to?
Yeah, I think if you raise your hand, I
Okay,
can
all
allow
right,
it
let's
to
do it
speak.
that way
Otherwise, yeah,
also.
feel free to use the chat box.
Yeah, thank you.
Yeah, I mean, I have one question. I mean, before somebody, maybe
Go ahead.
I think depend on some question. Maybe he can ask first, and then I'll follow.
Okay.
Yeah. Depend, you're allowed to talk. You can unmute yourself, and you can ask for question.
Yeah, can you hear me?
Yes.
Yeah.
Yeah, so we have this GFRP in our BRP research, so the point is how do we utilize in for our bridge structure, the deck and abutment, I see a lot of things like ductility issue and the fire hazard, so where we and how we can utilize in the best, so we can provide the more life to the structure.
Yeah, if I could just interject. I think there are design examples. So there has been published literature explaining what a typical bridge deck detailing is, and then how that process changes for to make it a GFRP bridge deck. So I think that would be the most obvious way to ease implementation into New
Yeah.
Jersey.
If I can
Yeah,
follow up.
because what we have seen, a lot of bridges, accident happens, a lot of places, because of the under clearance, the on and off, we have the emergency happens, something hit, but not every time fire hazard happens. But if we have to utilize this new technology, then we have to, because this is one of the side I would say we have to look into it, which can change our perspective, it affect the bridge, the fire hazard.
Yeah, I think
Yeah, I think it's accounted for largely. They definitely um, took a lot of consideration into that fact, and really all the things that are a detractor, they try to reflect that in the design guidelines to mitigate and address. So it is a concern, but that's why they changed the detailing to make it feasible and to implement. Yeah.
Okay.
so. I think Deepan, your concern is very valid, especially like for the fascia girder, for example, it gets hit many times and exposes the reinforcement. I think the guide, Mike, is mainly about reinforced concrete, right? And they probably did not touch on the like emergency type of situation, like a truck lighting on fire underneath the bridge. Is there any provisions for how to uh, change the design? Maybe we should add that in our project because this is something I think DOT is looking for.
I
Yeah.
believe that they do address that. Yeah,
Okay.
Thank you,
I believe
Professor.
there
Good.
is
Thank you, Deepan, for your
resources
question.
available.
Also, I have one more question, Professor.
Sure.
What is the unbonded when you use the GFRP and CFRP? Because I'm aware of pre-stress, bonded and unbonded.
So,
So how do you,
yeah, this is the CFRP is mainly for pre-stressing, and we were trying to look at post-tensioning because the idea is that if you want to, do a combination of bonded and unbonded, that could be a way to compensate for the fact that when you use bonded carbon fiber tendon, you might be losing on the ductility of the girder. When you are using them as an unbonded, you will also gain on. I mean, it's almost the similar behavior to steel because the unbonded tendon, does not rupture in a way, but the bonded, because of the strain that it allows only as 1.7%, then that's a very small strain to achieve the ductility that you need. So we were proposing a system where maybe to you could still use bonded steel tendons to get the ductility, but you can, especially in segmental type of bridges or in other bridges where you could still use the unbonded to be CFRP. So you don't have to do the unbonded being steel because that is susceptible to more corrosion. So the unbonded steel is not a from the durability point of view, is not something we would like to, it's something we'd like to replace if we can. And it works very well when you have a combination of steel bonded, like a pre-tensioned, and then you post-tension to, kind of a staged pre-stressing, so that you can utilize the slab as your part of the pre-stressing, then you can get maybe longer spans. This is a concept that in South Korea and some other, they have used that concept. They call it incremental pre-stressing, where you can use a combination of bonded and unbonded tendon in the same section, which is similar to what you do in segmental. So I think we looked into that, and it's very feasible to use bonded steel tendon with unbonded CFRP tendon, and the behavior we compensated for the ductility that you would lose if you use bonded CFRP tendon. Maybe this should be a topic for another webinar, but we just wanted to highlight the opportunity to also use, the carbon fiber, the Tokyo rope and the Aslan CFRP tendon for this seminar.
okay, thank you, Professor.
You're welcome. So, Mike, I have a quick note about the difference between AASHTO and maybe Daniel, maybe you can also, because you're involved in 440 like I am and ACI, but there is a difference in the fee factor of 0.75 in AASHTO, but 0.65 in ACI. The new code, the ACI 440.11, use the one on the left, whereas AASHTO used the one on the bottom, right?
Yeah.
So why is that? Why did AASHTO come up with a different resistant factor than the ACI? Is there something, maybe Daniel can highlight the difference if you're familiar with that?
I
Yeah, I'm not.
don't, go ahead,
Yeah,
Mike.
I'm not personally familiar exactly why. This was definitely something that was interesting and actually exactly why I included it in the slides, just to
Yeah.
highlight. I'm looking at both of the codes and that there is that discrepancy a little bit. But it does make sense why it would be 0.65 to me because that's what it is for compression controlled in steel. So that does make sense to me that it would be applied to compression controlled in a GFRP. But I did notice that in the code itself, and took that snippet out, that it is a 0.75. So I just wanted to
That's the
include
guide,
that
right? That's not the AASHTO LRFD. That's still a guide. It's not yet in the AASHTO
design guide. Yeah, so it's
LRFD.
the
It's
book
design guide.
on the left. Yeah.
Right. Do you know what year did that come out? Because the .11 code came out, I think, in 2022 edition, and it
Mhm.
took about maybe 5, 6, 7 years to come up with that one. Do you
Well,
know when the AASHTO code
yeah,
was?
it came out it's at the top right of the cover. It's 2018,
2018,
so just about
before.
2019, but yeah, from my understanding this is the most modern one in use
Mhm.
from what I saw.
Yeah.
Danielle, anything?
Yeah, this is the most modern. It is a guide and not in the code per se. Was not part of those conversations within the AASHTO committee
Right.
to be able to explain the differences between the two, but I could opine that, I mean, even a difference of 4 years in publication date certainly would have allowed additional research to be considered by ACI in putting forward, the factors that they had put forward.
Yeah, I think Carol Shields worked with Ted Galambos at Minnesota. They did the calibration for that. I'm not sure if the AASHTO guide did that part, but that's a big difference in a way for the industry to be able to, an AASHTO versus ACI. So this is something to look into why.
Yeah, 100%. And often there is
Yeah,
a synergy there, right? If
yeah,
ACI
absolutely.
maybe changes something, then AASHTO considers it and possibly adopts it, and vice versa.
Yeah,
AASHTO makes a change, right? I always like to joke the concrete doesn't know where it is, whether it's in a building or a bridge, right? So the behavior, obviously the loads are different and there are differences, but
sure.
in terms of the behavior, there's a lot that both groups can work together to try to harmonize.
Sure. There's a question in the Q&A. Yu Wang is asking, thank you very much for the wonderful presentations. GFRP and CFRP look very promising. You mentioned that creep and cyclic loading are addressed in the ACI code. Considering that these materials do not exhibit yielding like steel, do you think there are still any open questions regarding their long-term creep or cyclic performance that need further research beyond current standards?
Yeah, I could probably jump into that. I think there's definitely room for improvement, and I think it is a long duration test that takes a lot of time to really iron out any defects, and I think that's why it is a conservative point 0.3 of the design strength sustained. I think that's reasonably low. I'm not too familiar, but I think that is accounting for the lack of significant data to reinforce it.
So, I mean, if we were to do, I mean, further research on this, would it be on the creep of a flexural member? Because I think the creep of concrete is the same. So here, I think what this is implicitly saying that if you have two beams, one with a steel, one with CFR, I mean, with GFRP, and you load them both the same, which one would creep more, right? Is that
Yeah, and that
implicitly?
could lead
Mm.
to creep rupture, which isn't something that I'm incredibly familiar with. I
Yeah, you did your work
obviously
already.
I work a lot with creep, but not with the conjunction of creep rupture for rebar and especially
Yeah.
not GFRP. But I do know that a lot of the testing that comes out from these DOTs and literature is trying to address these tests. They have these very long duration tests on their alkali solutions or higher heat to try to accelerate the degradation.
Okay, great. Uh, Any other? I think we're coming close to the time, you know, on this, I want to thank everyone for the audience and their questions. If there are any questions, please email them to me or to Daniel or to Mike. I think this will be recorded and the emails are listed. We will be more than happy to answer this offline. With this, I'd like to thank our speakers, Daniel Kleinhans for her participation and you really added to our portfolio of resources. She's been very supportive of our work and we want to thank her and all the GFRP community for their approach. I want to thank our New Jersey DOT, the BRP program, for their sponsorship and allowing us to really delve into these topics, which are very much related to their work. And with this, I would like to thank you all, and we'll see you next seminar. I don't know
Yeah,
what is the date, but Lizzie or Chekhov, do we have a topic? I think we do, right?
yes, I think that just Lizzie just posted on the chat. There's a link that you can register. This is about the truck platooning impact on bridges, about the structural serviceability. So
Yeah.
for those engineers DOT who have some thought about this, it'll be great to join. It'll be the last Thursday of next month. It'll be 12 p.m. as of now. Hani Nassif will present, and with the other the engineers.
Just for me to give a background on this, this is a project that was sponsored by Federal Highway. The leading on this was Michael Baker International, and with Mujeski and Masters. So we were at Rutgers University. We worked, three of us, on this, and it came out a final report that was published by Cito Smart. It's available. Maybe we can put the link to that, Chekhov, in the chat if you can find it for the final report. But I will probably check with the time and the availability of the other speakers from Michael Baker, Brian Cozy, and also Tom Murphy from Mujeski and Masters to be also participating in this.
Yeah,
So
when I send the invitation, I'll include a link to download the report for those who are interested in.
All right. Thank you, everyone.
All right, thank you.
Okay.
Thank you.
All right.